Here's an example of conservation of angular momentum. We have a child of mass 30 kilograms stands at the edge of a small merry-go-round that's rotating at a rate of 1 radian per second. The merry-go-round is a disc of radius 2.5 meters and 100 kilogram mass. If the child walks in toward the center of the disc and stops 0.5 meters from the middle, what will happen to the angular velocity of the merry-go-round? Now we are assuming friction can be ignored. There are no external forces here. There are just forces between the child and the merry-go-round, but because they're both part of our system, they are internal forces and don't affect the angular momentum. So again, no external forces or torques means that angular momentum's conserved. So our initial angular momentum has to equal the final angular momentum. And as we know from our linear momentum, we have to take into consideration the momentum of each object before the change happens and as well as after. So the sum of the initial rotational inertia times the initial angular velocity equals the sum of the final rotational inertia times velocity. Right, and so in this case, we have the merry-go-round itself is rotating, but the child is rotating on the merry-go-round as well. So technically, we can think of this as we have two objects that are rotating, that have angular momentum. I went ahead and wrote this in. So the rotational inertia of the disk is 1/2 mr squared. And again, that's one of those formulas that would be given to us if we needed it on the AP test. The other thing we have to consider is the rotational inertia of the child. And we can think of them essentially as a point mass. And so we know the rotational inertia of a point mass is mr squared. So that object's mass times its distance from the axis of rotation squared. And so we can go ahead and start filling out kind of what's happening when the child is at that full radius of the merry-go-round. So over here, initially, we have the rotational inertia times the angular velocity, maybe we'll write it this way, of the disk, plus I omega for the child. Okay, and then likewise, we're going to have some symmetry. We're going to have the disk and the child after the child has moved as well. So these are both initial I omega, I'll say F, of the disk, plus I omega F of the child. All right, now we're getting somewhere. Now we just want to go ahead and put in those expressions for I. So I for the disk is 1/2 mr squared, and big M, big R, because that's what they used to describe the merry-go-round, times the initial angular velocity, then plus, let's see, the child was mass little m, but initially the child was at that same distance from the axis of rotation as the merry-go-round's radius. So we can use the same capital R here for the child's initial position. So big R squared times the initial angular velocity. So that's what's going on before the child moves. After the child moves, we'll have 1/2 mr squared omega final for the merry-go-round, but notice the rotational inertia of the merry-go-round didn't change. It's the same shape and size as it was before the child moved. And then plus the moment of inertia of the child, so mr squared little m, and let's call this little r squared, because now the child is not at the same radius as the size of the merry-go-round. So let's denote that with a different variable, and this is our final angular velocity. Now notice that I am using the same subscripts between the left and right hand side of the angular velocity. So over here I did label both of those the initial angular velocity, and we can think that the child is moving with the merry-go-round, and so we know they're going the same speed. So that's true both before the child moves and after the child has stopped moving. So because omega I on the left-hand side in both terms is the same, we could go ahead and factor that out and just kind of clean up our statement here. So we'll have 1/2 big M r squared plus little m r squared omega I, just factoring out that initial angular velocity. I'm going to be able to do the same thing on the final side as well, because again, the angular velocity of the child in the merry-go-round is the same. So do the same thing over here, 1/2 big M big R squared plus little m little r squared times omega f. All right, and we are looking for that final angular velocity. And so to isolate that, we see we could just divide both sides by this 1/2 big M r squared plus little m little r squared. So I'm going to write it all out in terms of the variables one more time, and then we'll put in some numbers. So with our rearranging, the final angular velocity is going to be 1/2 big M big R squared plus little m big R squared omega I divided by 1/2 big M big R squared plus little m little r squared. All right, so that would be essentially our answer in variable form. Now just putting in those numbers, 1/2, the mass of the merry-go-round was, let's see, 100. So 100, and the radius was 2.5 squared, plus the mass of the child was 30, and the initial place the child was at was also that 2.5. Make sure we square that as well. The initial angular velocity, they said it was rotating at a rate of 1 radian per second. So omega I is just 1. And then in our denominator, repeating, kind of filling in this huge expression here, 1/2 times the mass of the merry-go-round, 100, times the merry-go-round size, 2.5 squared. Again, that didn't change. Then plus the child, 30. But now the child is at 0.5 meters from the center. So that's the value we have to be careful of. All right. With all of this, we put it in the calculator carefully, and we get 1.6 radians per second. And so if we think of conservation of angular momentum, that makes sense. So when the child moved closer to the center, the rotational inertia decreased because the mass distribution is now closer to the center. That means that the speed increased.